Okay, so today we are going to start chapter 3 in the F3 book, differentiation. Okay, so first so in F3 book it's all about they're discussing about in this case they're discussing about differentiating hyperbolic functions. Okay, so previously we have learned all the rules in the P3 book, P4 book. You have learned about differentiating trigonometric functions, isn't it? So now in this book we are learning about how to differentiate the hyperbolic function. So first we'll write down these rules. So they have given you the formula that you need to know, that you need to remember to do the questions. So the first one is differentiation of sin x. So it's cos x. The differentiation of cos x is sin x. Do you see there's a difference between the trigonometric differentiation and hyperbolic? In trigonometric differentiation of cos was negative sign. Okay, but you can see in hyperbolic, we don't have that negative complication here. Differentiation of sin is cos, differentiation of cos is sin. Okay, answer differentiation of tan is h square. This looks similar, right? Differentiation of cot is minus cos h square. So these rules actually look kind of similar. Differentiation of cos h x is minus cot x cos h x. Yeah. So they all look the same as the normal trigonometric, right? So first of all, make a note of these rules because we will be using these rules to do the exercises. Okay, make a note of these rules first. Okay, so before we go to use the rules directly, let's actually try to do a proof of this rule. Okay, so in this example, they have done the differentiation of cos x with respect to x and shown how it becomes sin x. Shall we do it? So we'll do it manually. So cos x, we know cos x is equal to what? The hyperbolic functions were introduced to you in chapter 1, right? Cos x is ex plus e to the power minus x over 2. So basically what I'm going to do is I'm going to differentiate this cos x and we are going to generate the sin x function. Okay. So what is sin x, by the way? Sin x is ex. The difference is minus e minus x over 2, right? Right. So then I'm going to differentiate this cos x. We'll differentiate this function. Like we'll do the differentiation manually, and let's see whether we actually get sin x, because the rule is cos x differentiation gives sin x. So shall we differentiate? So I will differentiate cos x. D by dx means differentiating what? Differentiating cos x with respect to x. That's the meaning of d by dx. D by dx of cos x. So that means differentiate cos x with respect to x. So this side also d by dx means differentiate this particular bracket with respect to x. Okay, so shall we differentiate? So you all can see this denominator 2 is a constant. It's basically a half. If you want, you could keep it out and differentiate the inside. You could take the half out and differentiate inside. Ex plus e minus x. What happens when you differentiate ex? Ex differentiation is simply ex plus e to the power minus x when you differentiate. The rule, the differentiation rules. So these are the differentiation rules we learned in P3, right? So here EFX differentiation, second rule is EFX into f dash x. So these are the general rules I have given. So E negative x, the fx is negative x, which means E minus x into differentiation of that power, isn't it? The fx, which is what? E minus x, differentiation of minus x is minus 1. Is that okay? So basically it gives me, I can put the half inside over directly. Ex, this gives me minus e minus x over 2. So who is this? Basically ex minus e minus x over 2 is actually a sin x. So you can see that d by dx of cos x, which means when you differentiate cos x, with respect to x, we end up getting sin x. So this is the differentiation done by using the the definitions of the hyperbolic functions. Okay. So in the exam, unless they ask you to prove it, you are allowed to use these rules directly. Okay. Right. So then shall we go for the sums? Okay. Before we go for the sums, you must also know how to use the chain rule with these particular rules. Now you can see here they have given you differentiation of sin x, right? So this can be not just sin x. This could be sin 3x, sin 5x. So do you remember what we did in the trigonometric differentiation when you have sin 5x? So can you remember the rules in this set of rules? Can you see what we do? Yeah, so what we do here is basically you can see according to the rules I have given in this in the general form. So if you have sine fx, or basically like sine 3x, the differentiation is cos 3x into differentiation of that 3x. So into 3, right? So basically this is the chain rule. Okay, so the chain rule similarly can be applied to these rules as well. Okay, so chain rule can be applied. So you can see they have used it here. The d by differentiation of cos 3x is sine 3x into the 3. The differentiation of 3. So we could write the rules of the hyperbolic differentiation also in this general way. Shall we write it down in the general way? So differentiation of sine fx. Let's write it down quickly. So differentiation of sine fx. Basically, fx means a function of x. Okay, 3x. It could be ex. It could be anything. Okay. So when differentiate sine fx, what do we get? We get cos fx into f dash x. So this is me just generalizing it for you. Okay. Then differentiation of cos fx is equal to sine fx into f dash x. So likewise, continue the rules for everyone, because these are the rules that you actually need to use. Okay, so these are the rules that I have written in the generalized format using the chain rule. Okay, so now we will use these rules to do the exercises. Okay, let's go to the first one, exercise 3A, question number 1. Okay, so the differentiation of sine 2x. The differentiation of sine 2x. Let's start with that one. So sine 2x differentiation, what will it be? Sine differentiation is cos fx into f dash x. So basically sine 2x differentiation will be, sine differentiation is cos, right? And you write the 2x as it is, you do not change it, cos fx into the differentiation of 2x, which is 2. So basically it's 2 cos 2x. 2 cos 2x. Okay, the second one, cos 5x. Okay, try a few of these questions. Cos 5x, we'll discuss a few of them. We'll try these questions. So cos 5x, I have brought the rules here. You can refer it now. Okay, so cos 5x, when you differentiate, cos 5x is sine. You can see the 5x should come here into differentiation of the 5x. Okay, so it's going to be sine 5x into 5. You could write this directly. Like you can write the answer in one step as 5 sine 5x. Okay. The next one, the eighth one is x cos 3x. So in x cos 3x, the general rules of differentiation, they apply. Meaning now you can see you have here two functions of x. So when you have two functions of x, can we differentiate each one like directly? No, when you have two functions together as a product, you must use the differentiation product rule. Those rules still apply, which means when one person differentiates, the other one should wait. So which means in this case, if I keep x waiting, then cos 3x will differentiate to give me, cos differentiation is sine 3x into 3, right? Sine 3x into 3, and then it's a plus. Okay, so this is the differentiation of cos 3x that I did over here. In the next step, the cos 3x will wait while x differentiates. This x differentiates to give you what? The x differentiates to give you 1. Okay, can you see x differentiates to give you 1. So now write the answer. Final answer is 3x sine 3x plus cos 3x. Okay, then let's try the 10th one. So in the 10th one, it's again the same thing, right? X square. Okay, it's actually the same thing. X square cos 3x. So basically here again the product rule, x square stays while cos 3x differentiates to give you what? Cos 3x differentiates to give you sine 3x into 3x differentiation is 3. Sine 3x into 3. And then plus the cos 3x will stay while the x square differentiates. And it's x square now. So x square differentiation is 2x. So fix it and write. So I get here 3x square sine 3x plus 2x cos 3x. Okay, then let's try another one. Let's try these questions. Question 12, question 13, question 14, question 15. Okay, let's try these questions. So let me try question number 12. It's ln cos x. So to do ln cos x, of course, you need to remember the previous rules, right? The ln rules that you learned in the P3 book, you need to remember them also. So I've taken those rules also. Okay. So we need to have all these rules at hand. Okay. So now ln cos x. Okay, we need to differentiate ln cos x. So how do we differentiate ln cos x? You know the ln differentiation is given in rule number 3 here. Can you all see? The ln differentiation is given in rule number 3 here. So ln cos x ln differentiation is you can see the effects, the inside of the ln is in the denominator, and whatever the inside part differentiation is there in the numerator. Can you see? So ln cos x, what do you do? The cos x is coming to the denominator as per the rule. Okay, as this rule. Okay, the fx comes to the denominator. The fx is the cos x comes to the denominator, and then at the numerator you have the f dash x, which means the differentiation of cos x. So we know differentiation of cos is directly sin x. So basically it's sin x over cos x, which is tan x. Okay, so that is the differentiation. Okay, then the next one, the differentiation of sin x to the power 3. Now, you all should be able to realize that when they give sin x to the power 3, does it mean it's sin cube x? Is it sin cube x? Now, you all know if it's sin cube x, they put the 3 in the middle here. That means sin x whole thing to the power 3. No, this is actually sin, only the x has the power 3. Do you get this? This is just x to the power 3. The power 3 is not for the whole function. Okay, so then what do we do here? Just do the fx is the x cube here, sin fx. Fx is the x cube. So sin fx differentiation is what? Sin fx differentiation is cos fx into that into the differentiation of that. So then sin x cube differentiation is cos x cube, right? Into differentiation of the x cube, which is 3x square. So we end up getting 3x square times cos x cube. Okay, so remember when you see like this, the x power 3 belongs unto the x. Okay. Then the next one, 14th one, cos square 2x. Okay, so what happens in cos square 2x? So here obviously you realize here the power 2 is what? Belonging to the full function. It's not the angle that's squared here. It's the full function. Cos square 2x means cos 2x into cos 2x. Cos 2x into another entire cos 2x. So when you have like this, what is the rule we use? We can use the very first rule in differentiation. The very first rule is the power priority rule. So when you have any function to some power, the power is taken front, and then you keep the function as it is, subtract 1 from the power. After you're done with the power, only you differentiate the inside of the function. Okay, so that's what we do here. So cos square 2x, when I differentiate, I'll take the 2 in front, 2 times cos 2x, the first rule, n fx to the power n minus 1. So I take the 2 in front, cos 2x to the power 2 minus 1. Then into the f dash x means now what? The differentiation of the cos 2x. So cos 2x differentiation, again look at these rules. Cos 2x differentiation is what? Sin 2x, and don't forget the 2x also has to be differentiated again into 2. So that's gonna give us sin 2x into 2. So you could rearrange this and write it nicely. 2 into 2, that's a 4. Cos 2x to the power 2 minus 1 is simply cos 2x, right? 4 cos 2x sin 2x. Okay, is that okay? So this is the way we differentiate when the whole thing has a power. Okay, when the whole function has a power, differentiation of the power is what we need to do first, and then that means we use the very first rule of differentiation. This is the very first rule. Whenever there's a power, we go with this rule and then go to the associated rule inside afterwards. Okay. Then the next one, 15th one, e to the power cos x. So e to the power cos x is again differentiation of what? EFX rule, right? Can you see the EFX rule? E to the power fx rule says that differentiation gives you EFX into f dash x, right? EFX into f dash x. So basically E cos x differentiation is E cos x is the fx here, right? E cos x into the f dash x means the differentiation of the cos x, which is sin x. So this is it basically, right? So this is it. And then the differentiation of cos h x is of course given to you all. It's actually given the cos h differentiation and sin h differentiation was actually given to you, right? But however, they have I think in the 16th question they expect that we can actually prove. Now, what was the differentiation of cos h x? Cos h x differentiation was minus cot x cos h x, right? Shall we do that? Shall we do this proof manually? Can you all do this proof? The cos h x equation, can you all prove by using cos h x as 1 over sin x? Can you all actually prove that cos h x becomes minus cot x cos h x? Shall we try that one? So I want you all to differentiate cos h x is 1 over sin x. So basically your task is to differentiate 1 over sin x and show that you get minus cos h x cot x. So how do we do this one? One, you could use the, we could use the quotient rule or more than the quotient rule. I prefer I prefer doing like this. 1 over sin x, if I write like this, do you agree? Sin x to the power minus 1. Sin x to the power minus 1. The whole thing to the power minus 1. So now we can differentiate. So now d by dx of this cos h x. Okay, so we are doing the rule manually, okay? Instead of writing the answer directly in one go. So cos h x, the first priority goes for what? Whenever there is a power, we do the power first, right? Okay, so what I did here is once again, cos h x is 1 over sin x. We have the rule for cos h x. But the thing is, sometimes they can ask you to do the proof of the rule. Okay, so now we actually did the proof of this rule also, right? Differentiation of sin is first. We did it by using the hyperbolic definitions, right? So yeah, so likewise now the cos h x differentiation, they could ask you show that cos h x is minus cos h x cot x. So to do that, we could use the help of, okay, cos h x is 1 over sin. Then 1 over sin I could write it as the sin x whole thing to the power minus 1. And then now I can differentiate this because by using the power rule. So when you have a power, first, obviously the first priority goes to the power. What happens here? Minus 1 times sin x to the power minus 2. And then into sin x differentiation is cos x, directly cos. Isn't it? I told you sin differentiation is directly cos. So now let's fix this. I have a minus 1 here. Sin x to the power minus 2 means it's 1 over sin square x. Do you agree with me? Into cos x. Then let's break it minus 1 into, shall I break the sin square x as 1 over sin x into cos x over sin x? It's sin square, so I could have 1 over sin x into cos x over, basically I end up in the sin square x again, right? So who is 1 over sin x? Minus 1 into sin x is 1 over sin x is cos h x. Cos over sin is cot x. Tan x is sin over cos. Basically, the trigonometric rule also tan is sin over cos. Cot is cos over sin. So this is cos over sin is in hyperbolic, it's cot x. So this is what we wanted to prove, right? Minus cos h x cot x. Is that clear? So this is what we wanted to prove. Okay. So now you all can try question number 17. Try to do this, show that. Take a few minutes and try to do the show that. Okay, so once again, we'll discuss question number 17. If y equal a cos nx plus b sin nx, where a and b are constants, prove that d square y by dx square is equal to n square y. Okay, so d square y by dx square means you differentiate twice, right? Differentiate the first time, we get dy by dx equal a times cos nx. A times cos differentiation is what? Sin nx and then into n. Plus we have b times sin nx differentiation is cos nx and then don't forget into n. So basically, if I rearrange my dy by dx again, I end up getting dy by dx equals, let's take the an in front, an sin nx plus bn cos nx. Is that okay? So now let's differentiate the second time, d square y by dx square. So this gives me, shall I directly write? You know, the sin nx differentiation is cos nx into n, which gives me a n square cos nx plus bn is a constant. Cos nx differentiation is sin nx into n. bn square sin nx. I wrote the answer immediately, okay? And now the thing is, yeah, we can take n square out as common, and we get here a cos nx plus b sin nx. So a cos nx plus b sin nx is our y, and therefore we get d square y by dx square is n square y. Okay, is that okay? Right, then shall we move to the tangent and the normal question? So there was one question, question number 20. Okay, let's try question number 20. Okay, in question number 20, okay, then let's discuss question number 20. Find the equation of the tangent and normal to the hyperbola x square over 256 minus y square over 16. These are both squares. Equal 1 at the point 16 cos cube, 4 sin cube. Okay. So what do we do here? First thing to find the tangent and normal. This is exactly, I mean, this is what we discussed in the previous lesson, right? In the previous lesson, we discussed finding tangents and normals to hyperbolas and ellipses. So what do we do here? First thing is, so you need to look at this, x square over 256 minus y square over 16 equals 1. So differentiate with respect to x. What do you get here? I keep 1 over 256 aside, x square differentiation is 2x. 1 over 16 aside, y square differentiation is 2y to the power 1 into dy by dx. So this was completely discussed in the previous chapter, right? Differentiation of 1 is 0. That's why I did this immediately without much discussion. So I get here 2x over 256. I'll take this entire term to the other side as a positive. Is that okay? Plus 2y over 16 dy by dx. Is that okay? So we could cancel out the 2 to 2. And let me make dy by dx subject. So I end up getting dy by dx as what? The 16 comes on top, 256 is down, the x is up, the y comes down. Do you agree? 16 comes up, the 256 is down, the x is up over here, the y comes as division. Yes. So this is what I get for the dy by dx. So I need to get the gradient of the tangent at that particular point, right? So gradient of tangent is dy by dx. We can simplify 16 over 256. Yeah. Can I know the simplification of 1 over 16 to 16 over 256? It's 1 over 16. We could simplify our dy by dx a little bit further, right? Yeah. So dy by dx is 1 over 16 x over. Yeah. And then let's write the gradient of tangent. So gradient of tangent is your dy by dx, and I want to substitute my point. The point is 16 cos cube and 4 sin cube. So 1 over 16 x is 16 cos cube over sin is 4 sin cube. This is cos cube. Okay, so then I can cut off the 16 and I end up getting a dy by dx of the tangent is 1 over 4. Yeah, cos cube. Yeah. Over sin cube. Yeah. So we could see, yeah, we could leave it like this. And then let's get the equation of tangent. So the equation of tangent will be y minus y1 equal gradient times x minus x1. Y minus your y1 coordinate is 4 sin cube. Gradient is cos cube over 4 sine q. I mean, basically the same thing I have written. Into x minus x1 is 16 cos q. Then we can simplify. So this is basically the equation of the tangent. You could there is no particular show that they have given here. We can maybe simplify it a few more steps, because we've done the simplification in the previous chapter, right? 4y sine q. 4 sine q into 4 sine q is 16 sine square q. This is x cos q minus 16 cos square cube. So I think we remember in the previous chapter, cos square minus sine square is 1. And we did something similar to this in the previous chapter. Can you remember in the earlier one, in the earlier lesson? So then we get here, 4y sine q stays here. Minus 16 cos square cube comes as plus 16 cos square cube. Minus 16 sine square cube equals to x cos q. So you can see what happens here, right? 16, I can take it out. So when I take the 16 out, can you see what happens? The 16, I can take it out, and inside the bracket, you are remaining with cos square q minus sine square q. So you know this is cos square minus sine square is 1. So basically, this is the equation of your tangent. And then you could also find the equation of your normal. So to get the equation of the normal, all you have to see, it's at the same point, right? So a gradient of normal would be, yeah, reciprocal, the gradient of the reciprocal and change the sign. Gradient product is -1. M1 into M2 is -1. The simplest way to get the gradient of normal is to take the reciprocal of the tangent and change the sign, switch the sign. So I get negative because it's a positive. 4 sine q comes on top. Over cos q comes to the denominator. Okay, so the equation of normal, will be y minus y1 equal gradient x minus x1. So y minus y1 is, what was y1? 4 sine q, right? Y1 is 4 sine q. Gradient is minus 4 sine q over cos q into x minus x1 is, sorry, 16 cos q. Then we'll take the cos q to the other side. It goes as a multiplication. Y cos q minus 4 sine q cos q is sine, yeah. 4 sine q cos q minus 4x sine q plus 4 times 16 is 64 sine q cos q. Yeah, the minus 4 sine q cos q, we could take it to the other side. This minus 4x, I could take it here and like rearrange. Y cos q plus 4x sine q. 64 plus 4 is 68 sine q cos q. They haven't given us any particular format, so we could leave it in this manner. Okay, so this is it. Okay. Okay, so now we'll move on to the next part of our lesson, differentiating inverse hyperbolic functions. Okay, so they have given you the 3 hyperbolic functions: the differentiation of r sine x or sine inverse x, the differentiation of r cos x, and the differentiation of r tan x. Okay, so let's get started with these proofs. Shall we do the proof? The first one, the d by dx of r sine x. Okay, so let's write y equals r sine x And let's do the proof of r sine x is 1 over root x square plus 1. Okay, how do we do this? So y equal r sine x. You know, r sine x means, in other words, what? Sine inverse x. So sine inverse x means I could write this as what? Sine y equals x, isn't it? Sine inverse x means, in other words, sine y equals x. Okay, so now let's differentiate with respect to x. So when we differentiate with respect to x, what happens? When you differentiate with respect to x, the sine y differentiation is, the sine differentiation is cos, sine y is cos y, but then into y, right? Into y differentiation, because you're doing with respect to x, into y differentiation is dy by dx equals differentiation of x is 1. So basically you get dy by dx is 1 over cos y. But you can see to show that for dy by dx is some 1 over root x square plus 1. So how do we get that? Show that. So we know the rule. Cos square minus sine square is 1, right? Cos square y minus sine square y is equal to 1. And we know now our sine y is x. Can you see? Sine y is x. Therefore, sine square y will be what? It will be x square. Do you agree with me? Yeah. So basically, cos square y is 1 plus x square, which means cos y, removing the square, root 1 plus x square, and that's how you get the root in the denominator. So dy by dx is equal to 1 over root 1 plus x square. So that's the proof of y equal r sine x. Similarly, shall we start the proof of y equal r cos x? Shall we start the proof of y equal r cos x? So that's right. That's right. So the first thing we do is we write what? Cos y equals x. And then let's differentiate with respect to x. So when we differentiate with respect to x, what do we get? What do we get? The first differentiation is sine y into y differentiation is dy by dx. X differentiation is 1. And then the differentiation of x is 1. This is okay. Basically, we get dy by dx equals 1 over sine y. So then what is sine y? Again, we have the same rule. Cos square y minus sine square y equals to 1. Sine y, right? So basically, in this case, the cos y is only equal to x. Okay, so cos y is equal to x, which means cos square y is x square minus sine square y equals 1. We get x square minus 1 is equal to sine square y, which means sine y is root x square minus 1. So basically that means we get here dy by dx is 1 over root x square minus 1, and this is the show. Okay, so this is the result that we proved that we have over here. Okay, and then I think you all draw in r cos x. You remember the graph that we drew in chapter 1, right? In the r cos x graph, it's defined for x values greater than 1. That's why they have given here x is greater than 1. These are the domains of the r cos x graph. R sin x graph also is drawn. It doesn't, it has all real values of x. R cos x graph has a domain x greater than 1. R tan x has the domain modulus x is less than 1. So these things were discussed in chapter 1. Okay, anyway, let's get the proof of r tan x. Y equals r tan x. So when you differentiate, r tan means it becomes tan y equals x. Okay, let's differentiate now. So when you differentiate tan, what do you get? Tan differentiation is sec square y. You are differentiating with respect to x. So y differentiation is dy by dx, because it's sec tan fx is sec square fx into f dash x. So basically sec square y into dy by dx equals x differentiation is 1. So I end up getting here dy by dx is 1 over sec square y. So now let's write the equation relating sec square y and tan square y. So the trigonometric equation is 1 plus tan square is sec square, right? 1 plus tan square y is sec square. Do you remember? And then by using Osborne's rule, we convert the trigonometric to hyperbolic, right? Any sign product or implied sign product is negative. So tan has a sign product, tan square has two tans multiplication. Each tan has a sign inside, sine over cos, sine over cos. So there's a product of sign here. So basically the hyperbolic identity would be 1. It's not plus, it's minus tan square. Y equals sec is a product of cos. So the product of cos doesn't become negative. Sec square y. So these are rules you learn in chapter 1. Okay, 1 minus tan square y, sec square y. So basically we learn tan y is x, which means 1 minus x square is sec square y. So I have the sec square y, which gives me dy by dx is 1 over 1 minus x square. 1 over 1 minus x square. Okay, so these are the proofs. These are the proofs of all these three rules that we are about to use. Okay, and then the next thing that I want to know is to use these rules in their general format. What do I mean by the general format? So these rules, they can give this as r shine 2x, r shine ex, r shine, I mean, they could change the x inside, right? So when they change inside, you must be able to use the what rule? You must be able to use the chain rule. So let me give it in the more generalized format. So if you differentiate r shine fx, the differentiation will be 1 over root fx square plus 1 into the f dash x. Are you all with me? If you are differentiating r cos fx, the differentiation it would be 1 over root fx square minus 1 into f dash x. Do you see what I'm doing here? Basically, you need to differentiate the fx function again, right? Into, so this is the chain rule. And r tan fx is 1 over 1 minus fx square into f dash x. Okay, so these are the generalized rules. So now what we need to do is we need to use these rules and do the questions. Okay, so let's go for the exercise 3b now. Okay, so exercise 3b, question number 1. The differentiation of r cos 2x. So what happens when you differentiate r cos 2x? So directly let's use the rule. Differentiation of r cos 2x is here 1 over differentiation of this is fx square, right? Fx is the 2x. Fx is the 2x, so which means we get here what? 2x square differentiation is 4x square minus 1. This rule, right? 4x square minus 1 root into the f dash x is the 2x differentiation. 2x differentiation is 2. Basically, it's 2 over root 4x square minus 1. Is that okay? Then the next one. Then the next one. Part C. I have highlighted part C. Let's differentiate r tan x, r tan 3x. So r tan 3x differentiation is 1 over 1 minus 1 over 1 minus fx is the 3x square. So 3x, when you square 3x, you get 9x square. Is that okay? Into f dash x is the 3x differentiation, which is 3, because yeah, fx is 3x. So fx squares here, and this is the f dash x here. Do you agree with me? So we end up getting for part C 3 over 1 minus 9x square. Is that okay? The differentiation shared answer. Next one, part E. Part D. Okay, part D is going to be a little bit of a challenge. They ask you to differentiate R set checks, right? So have you done R set checks? Have I given you a rule for R set checks? No. So for R set checks, what we'll do is we will create the rule like the way we did the others. So r such x. So let's say let y be equal to r such x. The way we did the proofs for the earlier sums. For r cos, r tan, r sin, we did the proof, right? In the manual way. So similarly, let's do it for this one also. Y equal r such x. So what happens here? R such x means this is such y. Such y equals x, right? Such y equals x. Now let's differentiate. What happens when you differentiate such? Such differentiation is, so the rule we did previously, right? Such differentiation was what? Can I know such differentiation? Such y tan y, right? Minus such y tan y, and then into differentiation of y is dy by dx equals differentiation of the x is 1. Okay, then let's make dy by dx subject. Dy by dx is 1 over minus such y tan y. Is that okay? Okay, so the minus mark I could take it out front even. Okay, so then the thing is we need to keep our answer not in this manner, right? Our answer needs to be in terms of x. So you need to find ways to replace the tan y and the such y. So what you can do here is you can see definitely such y is what? X. So such y we can replace it x. The only thing is to find the replacement for tan y. How do you find the replacement for tan y? We know the rule 1 minus tan square. 1 minus tan square y is such square. We just used this rule a few moments ago, right? 1 minus tan square y is such square y. So such square y is x. So such square y is x square, which means basically 1 minus x square is tan square y, which means tan y is root 1 minus x square. Is that okay? Then our dy by dx is ready. Dy by dx equals minus 1 over such y is directly x, okay? And tan y is root 1 minus x square. So this is the dy by dx of the differentiation of r such x, okay? Then the next one, part I. Part E. We have to do part E, right? Part E, you are supposed to differentiate r cos x square. So let's differentiate r cos x square. This one you could do it directly by using the rules, right? So do it directly. R cos x square, we can directly use the r cos fx rule, right? Isn't it 1 over root fx square minus 1 into f dash x? We could use this rule directly. So let's use it. Okay, let's use the rule. The differentiation of r cos fx is 1 over, it's the root of, you have to square your fx, right? So here fx is x square. When you square x square, you get x to the power 4. Okay, minus 1. Then into the differentiation of your fx. Your fx is x square. Differentiation of x square is 2x. So basically you end up getting 2x over root x to the power 4 minus 1. Okay, then the next part was part I, right? In part I, they wanted you to solve e to the power x cube r sin x. R sin x of 3x. Or e to the power x cube r sin x. Okay, so this is basically what you can see. There are two functions of x here, right? And it's a product. So you must use what rule? You must use the product rule. So basically one person stays while the other one differentiates. So let's do this one. The differentiation of this guy is d by dx means we differentiate with respect to x. So EX cube stays, while R sin X, when you differentiate, you get what? 1 over, no, I'm keeping EX cube waiting. The R sin X differentiates. R sin X differentiation is 1 over root X square plus 1, right? 1 over root X square plus 1 into X. X differentiation is 1, so we don't need it, right? Then plus, now the R sin X weights. Now the R sin X weights, while EX cube, when you differentiate, it's EFX, right? EFX, when you differentiate, it's EX cube into FX. The FX is X cube. So X cube differentiation is 3X square. Can you see how far this goes? So basically it's EX cube over root X square plus 1 plus uh, plus 3X square EX cube into R sin X. Okay, so this is the differentiation. Okay, so after that, the next question says to prove that the differentiation. Okay, so these two proofs we just did it, right? So we don't need to do that. We have already done it. Okay, now let's go for question number 3. Okay, start question number 3. Given that y equal r times ex over 2, prove that. Okay, you need to prove this equation. Shall we try to prove this? Okay, y equal r times ex over 2, differentiate. Y equals r times ex over 2. Let's differentiate this. Okay, so then to get we need to get this show that, right? Okay, so how do we get the show that? First you need to differentiate. Okay, so when you differentiate dy by dx, what do we get here? Dy by dx equals r times ex over 2. It becomes 1 over, yeah, fx is ex over 2, right? So 1 over 1 minus fx square is ex over 2 whole thing square. Are you all with me? And then into you have to differentiate the ex over 2. So basically it's half times ex differentiation is ex. Okay. So now all you need to do is you have to kind of like get this show that you have to rearrange the equation and get the show that. So let's rearrange. I get here dy by dx equals 1 over 1 minus ex square over 2 square is 4, right? 2 square is 4. Okay, and then that whole thing into half ex. So work on this. Dy by dx equals 1 over, I can take the common denominator here, right? So then I can multiply this with 4. So I get here 4 minus ex square means the powers multiply. That is e2x, right? Because the power is multiply, x and 2 multiplies and you get e2x over 4 into half ex. And what happens to the 4? The 4 is in the denominator's denominator. Like basically the 4 will go up. So you end up getting for dy by dx 4 over 4 minus e to the power 2x times half e to the power x. So 2 and 4 cancels. 2 times 1 is 2, 2 times 2 is 4. Is this to show that? Yeah, they have taken 4 minus ex to the other side. So when you take 4 minus ex to the other side, we get 4 minus e2x times dy by dx equals 2 times ex, which is our show that. Okay, so this is our show that. Okay, let's try the fourth one as well. Let's quickly try the fourth one. Question number 4, given that y equal r sin x, show that 1 plus x square, okay, d cube y by dx cube plus 3x d square y by dx square plus dy by dx equals 0. Basically, you differentiate the thrice, right? Because we have d cube. Shall we try? So y equal r sin x. Okay, so let's differentiate dy by dx. What is the differentiation of r sin x? The differentiation of r sin x. So these are the rules. R sin x differentiation is 1 over root x square plus 1 into, yeah, that's it, right? 1 over root x square plus 1. right? Then let's differentiate, keep on differentiating. I think before I go for the second derivative, what I'll do is I'll take the root x square plus 1 to the other side. Or else, there are two approaches here. You could try differentiating, like you could get dy by dx, d square y by dx square, d cube y by dx cube, by keeping this dy by dx a subject and actually substitute those three values into this equation and get the show that the answer becomes 0. That's one way that you could do this. The other way is really hard, where you try to derive this, like where you try to work on and where you try to derive it. That's going to be a bigger challenge. So if you want to derive it, I think the best thing you could do is you could take root x square plus 1 to the other side and then go for product rule and keep differentiating again. Or the other option is I could keep it like this, get d square y by dx square by using the quotient rule here. And then again get d cube y by dx cube and just substitute it to the equation. So what I'll do is I'll do it in the other way. I mean, any of these approaches are correct, okay? Root x square plus 1 times dy by dx equals 0. Is this okay? So now what we'll do is we'll differentiate this with respect to x. It's going to be the product rule. So with product rule, when you differentiate, what happens? The root x square plus 1 will wait. When dy by dx differentiates, it gives you d square y by dx square. Okay? And then go for the next one. This is not equal to 0. This should be equal to 1, right? Yeah. We move the root x square plus 1 to the other side. It goes as a multiplication. This will be 1. Okay, yeah. And then I applied the product rule. Root x square plus 1 stays. D square y by dx square. Now, the dy by dx is staying. The dy by dx stays. Root x square plus 1 means you give priority for the power, right? Root means it's a x square plus 1 to the power half. So when you differentiate, first priority goes to the power half times x square plus 1 to the power half minus 1. Isn't it? To the power half minus 1 gives you minus half. And then after you're done with the power, this is the first rule of differentiation. After you're done with the power, go and differentiate the inside. So that the inside differentiation, x square differentiation is 2x equals 0. This time it's equal to 0 because we differentiate 1 and that becomes 0. Okay, so now rearrange this equation. What I would do is I would probably multiply the whole equation with root x square plus 1. So rearrange this equation, try to get the show that. Okay, so the next thing that I'm going to do is I'm going to rearrange this equation. Okay, so I get here root x square plus 1. Okay, root x square plus 1 into d square y by dx square. Plus I can cut the 2.5 here. So I end up getting here x times dy by dx times x square plus 1 to the power minus half equals 0. Okay. And then we multiply the whole equation with the root x square plus 1. Multiply the whole equation with root x square plus 1 and we end up getting root x square plus 1 into root x square plus 1 is, you get directly the x square plus 1, right? Into d square y by dx square plus x dy by dx times the root x square plus 1 with the x square plus 1 to the power minus half basically gives the power 0, right? Because this power plus half, power minus half multiplies to give you the powers will add and gives you power 0. They cancel off basically. So that's it, equals 0. 0 times root x square plus 1 is 0. So then we are halfway there to show that now I need to differentiate this guy once more, right? To get the d cube y. So let's differentiate once more. So again, I have product rule. In here also there's a product rule. Here also there's a product rule. Are you with me? So differentiating once more. So let's differentiate once more. X square plus 1 weights while d square y by dx square differentiates to give us d cube y by dx cube. Okay, now plus the d square y by dx square is weighting now. In the product rule, this guy weights while the x square plus 1 differentiates. So what do you get for the differentiation of x square plus 1? Simply 2x. I don't need to put the plus 0, right? 2x plus 0. Basically just 2x. That's done. Now apply product rule for the other guy. Here plus the x is weighting. dy by dx differentiates to give you d square y by dx square. And then plus now the dy by dx weights while x differentiates to give you 1. The x differentiates to give you 1 equals the differentiation of 0 is 0. So it's just rearranging this and you get to show that nicely. X square plus 1 times d cube y by dx cube. We can add, we have here 2x d square y by dx square and 1x d square y by dx square. Simply it both adds to give you how much? 3x d square y by dx square. Added the two like terms here. These two terms are two like terms, okay? Added them and then plus dy by dx. Is this our show that? Yes, so this is the show that. Okay, so 7 marks show that. Okay, so we are done with this part. So now we'll move on to the next part.